Okay, let's go ahead and get started. Just a couple administrative announcements. I have here the final problem set for you guys to pick up, which will be due next Wednesday. I won't be handing out any other problem sets. I will probably hand out some practice problems for the final exam. Would that be helpful? Would you like that? You would like that. Okay, I'll go ahead and do that. The other announcement, I'm actually going to be out of town on Friday, so I've arranged a super special secret surprise guest lecture. It's a different one, a different secret super surprise guest lecture from last time. But it's actually on something not really related to the subject of the course. Well, it is related to the subject of the course, it's modern physics, but it's outside of the standard curriculum. So it's going to be a lecture on particle physics, sort of a gentle introduction to our current understanding of particles, what particles are, what Feynman diagrams are, what virtual particles are, all of that stuff. So I've got a actual real live professional physicist coming in to tell you all about that on Friday. Okay. And I guess the other thing I should say is I won't actually, because I'm out of town, I won't have my office hours on Friday at the usual time. If you do need to come see me about something, you can always send me an email to set up a time to meet or talk to me after class. Okay. So let's continue with our development of the theory of quantum mechanics. So we've seen in this class that electrons, and indeed many other sorts of particles, but in particular electrons, because they're the easiest to study experimentally, exhibit two characteristic features that make us think that they should be described by waves of some sort or another. So we first saw in our discussion of the double slit experiment that electrons exhibit interference. So in particular, if you took some source of electrons and shined through a wall which has two slits on either side, then if the electrons behaved like particles, you would think that they would go through either one slit or the other, and so that the pattern that they would form on the screen on the right-hand side of this diagram would just have two peaks, one peak corresponding to electrons going through the upper hole, and another peak corresponding to electrons going through the lower hole. But instead, what one finds, if one does this experiment, is that the probability of seeing an electron on the screen here exhibits the same sort of pattern that we see when you would, for example, shine light through two slits or study the propagation of water waves through two slits in some sort of barrier. In particular, we see interference effects. So you see peaks and troughs in the pattern of probabilities of the electron arriving on the screen, which tell us that somehow the electron is going through both slits simultaneously. And in doing so, the different paths that the electron can take through either the upper or the lower slit are interfering with one another, the same way that light will exhibit interference. And the other feature that we saw that taught us that electrons behave at least a little bit like waves is quantization. So in particular, if you have a nucleus, such as the nucleus of a hydrogen atom, then the allowed states that an electron can occupy as it orbits around the nucleus of this atom are discretized in some way. So in particular, the allowed radius that the electron can have as it goes in one of these circular orbits can take only one of a discrete set of values. So this is something that we discussed last time in the context of the Bohr model of an atom. So in that case, we saw that the radius that an electron could have was quantized so that it had to be h bar squared over mc, where c was a constant that told you about the strength of the electromagnetic potential that's pulling the electron to the center of this atom, times the square of some integer n, and the velocity was likewise quantized in such a way that the total angular momentum of the electron, which is mvr, that's just the angular momentum of an object that's going in a circular orbit, is an integer times Planck's constant, h bar. And this has a very nice physical interpretation in terms of the wave picture of an electron. If we remember that an electron should be described as a wave with a wavelength, lambda, that depends on the momentum of the electron. So if one takes this picture of an electron as a wave and combines it with the Bohr model, you'll see that, in fact, these allowed radii are precisely those for which the radius is a multiple of the wavelength. Or sorry, I should say the circumference, that is to say the total distance the electron travels as it goes through one orbit, is a multiple of the wavelength. And in this way, we see that quantization and interference are really the same thing. Okay? Because you can imagine this electron orbiting a proton, say, at the center of a hydrogen atom. And as it does so, the wave associated with the electron oscillates with some characteristic wavelength. And as you go exactly one orbit around the proton, if the wave exactly comes back to itself, then you'll have constructive interference. But if it doesn't come back to itself, then you'll have destructive interference. And you can see that these special quantized values of the radius allowed by the Bohr model of the hydrogen atom are precisely those for which you have constructive interference when the electron, as for each time the electron orbits the electron, proton. What I've presented to you so far in this course over the last week or so are a set of experimental results and a set of models that people developed, de Broglie, Bohr, Einstein, and so forth, in the early days of the 20th century, that allow us to develop some sort of picture for what is going on inside of an atom. But what I would really like to get to over the remaining 5 or 6 classes that we have left to us this semester is a more precise understanding of exactly how it is we describe an electron in quantum mechanics. And so to that end, I would like to begin telling you precisely exactly what variables we use to describe the electron. I've told you that electrons behave like waves, but I haven't told you exactly what the equation is that governs those waves, nor what the interpretation of those waves is. That's something that I want to start developing now. But before I do so, let me just pause and see if there are any questions. Yes?
So the quantization of possible wavelengths comes because we define it as the multiple of the circumference of its orbit around the proton.
That's right. So
what happens if you have a free electron?
Excellent. Okay. If you have a free electron, so remember, so the way that one should think about quantization is as follows. So if you want a simple mechanical model, you can think of your guitar string. And if you have a guitar string of a finite length, then you'll have the allowed frequencies, which are all multiples of some basic frequency. Okay. But if you have an infinite guitar string, then any frequency is allowed. Okay. Likewise, if you have an electron which is confined to a box, okay, say that the electron is bouncing between the two sides of a box back and forth, then the allowed frequencies of the electron and hence the allowed energies of the electron will be discretized. or if you have an electron in an atom so that it's going back and forth around the atom and it's coming back to itself after some period, then its energy states will be quantized. But if you have a free electron that can move wherever it likes, then its energy states will not be discretized. They will not be quantized. And indeed, that is what we see all the time. So for example, a metal, the definition of a metal is that it is a lattice of atoms which has lots of electrons that can move around freely. And that explains why it is that metals are conductors. Okay. Because electrons carry charge, and if an electron can move around freely, then it's easy to transport charge from one place to another. Okay. So for example, in a metal, that's by definition a system which has lots of free electrons. Okay. Or for example, in particle physics, if you have scattering experiments with free particles, then of course you'll see the same thing. Okay. Good questions. And we'll come back to the free electron and how we describe that in quantum mechanics in a little bit. Yes?
But the de Broglie wavelength is the momentum classical?
Yeah, so the de Broglie formula is some sort of ad hoc, it's not something, how should I put it? It's a model, okay? It's not a theory. There's not a theory behind what the de Broglie wavelength is per se. It's a model that you should keep in mind if you want to do some sort of back of the envelope estimate for how particles and other objects behave as waves. Then the de Broglie model tells you what wavelength you should be using. And indeed, P here is just the classical momentum of the electron. Now, one could, of course, try and use relativity and use a relativistic momentum there. Once you include quantum mechanics and relativity at the same time, life gets much, much more complicated. So typically, and indeed, many of the things that I'm saying to you today are no longer true. So for that reason, usually we only apply the de Broglie formula in the context of classical systems, or non-relativistic systems, I should say.
By 2 pi somewhere.
Oh, I'm sorry. Is there a 2 pi somewhere? Probably.
The J equation, and you divide both sides by mv, then you have nh over mv, which is nh over v.
Okay.
Which is n lambda.
Did I make some mistakes somewhere?
I don't think it really matters.
I don't think it really matters. Okay, let's pretend I didn't make any mistakes anywhere. Sorry about that. Yeah, I might be off by some 2 pi's or something here. There's actually a funny piece of history. So de Broglie wrote this paper proposing that his formula for the de Broglie wavelength, and it was 1 page long. Okay, and it turned into, and he won a Nobel Prize for it. And so I think it's the only case I know of where someone's been able to win a Nobel Prize for a paper that's 1 page long. It was also his PhD thesis. So if your PhD thesis is, most PhD theses, the quality of a PhD thesis is inversely proportional to its length. Okay, so I think that it's not a bad day when you can write a 1 page PhD thesis. Good. Any other questions? Yeah. It might have been 2 pages. I don't actually remember. I guess it depends on what font, whether it was what font he was using. Okay. Good. Okay. Yeah. Yeah. I'm sorry. There might be some 2 pi's there. Okay. Good. So, what then is the appropriate variable that we should be using to describe the dynamics of an electron? When we talk about a wave, like when you talk about light as a wave of electromagnetism, you know what the variable is that is fluctuating, that is oscillating. In particular, it's the electric and magnetic fields that are oscillating, that make up a light wave. Likewise, for a water wave, you know what the variable is that's oscillating. It's the height of the water away from its equilibrium position. Okay. So for an electron, or more generally, for some sort of particle in quantum mechanics, we describe its dynamics by a variable which is referred to as a wave function, typically denoted psi, that will depend on position and time. So just as the electric field in some system will depend on position and time, and light is described by some oscillations in that electric field, we would like to describe an electron, for example, in terms of some function psi, and the oscillations, the waves in psi of x and t, will describe the wave behavior that I've been discussing over the last few lectures. And here I've written x just as one dimension. So if I were describing an electron moving in one dimension, then I would just have psi as a function of one variable, x and t. Or I could write psi as a function of three positions, x and t. So as a function of a vector x and time t, if I want to describe an electron moving in three dimensions. Okay. Now, normally, of course, I would be interested in describing an electron moving in three dimensions, say, for example, in the hydrogen atom. But very often, to keep equations simple, we will restrict our attention, in this course at least, to objects that are moving just in one dimension. Okay. So, for example, an electron moving in a wire would be a good model for something moving in one dimension. Okay. And what do we know about the wave function of an electron? We know that it should obey some sort of linear equation of motion. Because remember, the salient property that waves have that make them interesting to study and allow them to exhibit interference, diffraction, and so forth is the fact that you can take one solution, one wave, and another wave, and you can add them together to get a third wave. Okay. And because of that, you know that, and that follows from the fact that the wave equation, the equation that these waves satisfy, is linear. Okay. You can take two solutions to the wave equation, add them together to get a third solution. And so what we would like to do is just guess using basic principles and a little bit of sort of educated guesswork exactly what the equation is that this function psi should satisfy. So in order to determine exactly what equation it is that this function psi should obey, I'd like to go ahead and step back a little bit and remind you of precisely what it is that precisely how it is we interpret psi physically. So let's imagine that we're performing some interference experiment. Then the quantity, so we're shining some electrons through two slits in a wall, and we have a screen over here. And what we actually see when we perform a measurement is the probability that the electron will arrive at some particular point on the screen. So what we actually observe when we see this interference pattern is a probability. And in particular, it's a probability distribution. And the question that we would like to ask is, what is the relationship between that probability distribution and the wave function psi, which we're going to use to describe the electron? So the first thing that I would like to point out is that psi can't be the probability itself. You would like to interpret psi as the probability that you have an electron at a position x and at time t. But psi cannot be that probability. It can't be that probability because probabilities are positive numbers. Okay? Probabilities are positive real numbers. And in order to have things interfere with one another, in order to have destructive interference, you have to be taking a positive number plus a negative number. So if psi were only positive, and we were looking at, and for example, the total wave function for the electron would be some psi associated with the electron going through the positive slit, and a psi associated with the electron going through the negative slit, and then the total wave function were the sum of those two, if each individual psi was a probability, then you would never get destructive interference. So, since probabilities are positive, the probabilities themselves can't obey destructive interference, or can't exhibit destructive interference. And instead, the probability that we see an electron at a given position and time should be determined by psi in some way, but it can't be the value of psi itself. Because in order to have destructive interference, psi must be allowed to be both positive and negative. And in order to understand exactly how it is probabilities are related to this wave function, I'd like to remind you of something we already know. And in particular, I'd like to remind you of how this works for electromagnetic waves. So let's just remember how things work with light. For electromagnetic waves, the thing which obeys a wave equation is the electric field, E. So it obeys a linear equation so that if E1 and E2 are solutions to the equations of electromagnetism, then so is the sum E1 plus E2. But what we actually observe when we observe light on a screen, say in some diffraction experiment, is not the electric field itself, but rather the intensity or energy of an electromagnetic wave is proportional to the square of the electric field vector E. So, for example, you could imagine that you have one field E, E1, and another E2. E1 and E2 can both be either positive or negative. And so, when you calculate the total intensity of the sum of E1 and E2, that's positive, but it can also be 0 if E1 is equal to precisely minus E2. So if you have a quantity E that obeys a linear equation, the interference that we observe actually shows up in the absolute value squared of that electric field. So in particular, it makes sense to identify the probability that an electron is at a position x at time t, not as the wave function itself, but as the absolute value squared of the wave function. And just to reiterate, the reason why we do that is that in order to have something fluctuate, oscillate in time, it has to be able to take either positive or negative values. If psi is going like cosine omega t, then as t proceeds, psi will be first positive, then negative, and so on and so forth. But probabilities are always positive. It doesn't make sense for me to say that the probability of observing an electron here is -2. Probabilities are numbers that are positive and take values between 0 and 1. So we therefore identify the wave function not as a probability, but as something that you square to get a probability. And in particular, it's not precisely a probability, but rather a probability density. So what do I mean when I say that psi is a probability density? What I mean is that, in particular, if you take psi of x and t, and you want to calculate the probability that that the electron is sitting within a small box of size dx and time interval dt around the point x and t, then that probability is psi of x of t, the square of psi of x and t times dx cubed dt, or sorry, I guess I'm working in one dimension. Okay, so it would be dx dt. So that is the probability that the electron is sitting in okay, let me write it this way. The psi squared times dx is the probability that the electron is sitting in the interval between x and x plus dx at time t. We could also talk about an interval in time, but that, I think, is not necessary for what I'm going to talk about today. So is what I mean by a probability density as opposed to a probability clear? So just to make that a little bit more clear, for example, the probability that the electron is sitting or is at a position x that is between two values x1 and x2 is the integral between x1 and x2 dx of psi squared. So, and more precisely, the probability that the electron is anywhere is the integral from minus infinity to infinity of psi squared, which should be equal to 1, because that electron's got to be somewhere. So if we're describing the wave function of a single electron, then we want to, if we're describing the dynamics of a single electron, then we do so by writing down a wave function that depends on x and t. And the characteristic properties that this wave function has is that, first of all, it obeys some linear equation, so that you can add two solutions together to get a third solution. And second, that if you square it, you get the probability density that the electron is sitting in a small neighborhood of the position x at time t. And the fact that we're talking about one electron just means that if you integrate this absolute value of psi squared dx from minus infinity to infinity, you should just get 1. Now, I've written these formulas here for an electron moving in 1 dimension. If I wanted to, I could write down these formulas for electron moving in 3 dimensions. In that case, it would be an integral d3x. Psi would describe the probability density that you live in a small box of size dx times dy times dz around a point with a given value of x, y, and z. So I'm now going to use this formula here to guess what sort of equation it is that psi should obey. But before I do so, let me pause and see if there are any questions. Yes?
Yeah, suppose we have a free electron, so the probability to be at any point is the same?
Yes. So in particular, so a free electron is a little bit subtle in that if you have an electron that can be absolutely anywhere in space, the probability that it should be at any given point is infinitesimally small, right? So in that case, you have to be a little bit more careful, and you have to the way that we describe it is a little more mathematically sophisticated. There's nothing particularly deep about it. It's just a little more technical. So the way that you should think about this a little bit, if you to have a little simpler example to think about, is just an electron that's, say, confined by some potential. Let's say an electron in the neighborhood of a proton. So the pull of the protons, the positive charge of the proton is keeping the electron confined to be in some region, so it's not going to fly off to infinity. Or if you want to think more simply, you could just say the electron's in a box. Okay, and then the probability of being at any given point is going to be positive, but not necessarily equal to 1. Question?
So, say this is the experiment with double slit.
Mm-hmm.
If the electron can be anywhere, how can we differentiate between that electron? Imagine if another electron in this place, how can we know that
Okay.
it's that electron?
Yeah, I mean, so in this class, I'm going to describe to you the theory of what is called single particle quantum mechanics, okay, where we just have one electron. So what we're imagining is a double slit experiment where you have a source, you emit one electron, and you have a screen, and you want to see where the electron goes. And you want to calculate the probability that it arrives at a particular point on the screen. Okay. Now, if you want to be more sophisticated, you could talk about, well, there's also the probability that I could emit, maybe you want to emit 2 electrons, or 10 electrons, or 1,000,000 electrons. And then you have to worry about which electron it is you're studying. You have to worry about, I don't know, that electrons could be created or destroyed. You need to worry about a lot more stuff, okay? In its simplest incarnation, all of the important details of quantum mechanics, all the important conceptual things that go along with quantum mechanics appear when we just talk about one electron. So that's what I'd like to focus on. Indeed, one of the reasons why relativistic quantum mechanics is so difficult is that when you add special relativity to quantum mechanics, you're forced to consider the possibility that electrons could be created or destroyed. Okay. So I want to forget about those subtleties for the purposes of this class. Are there other questions? Yes?
Does this equation only give us probability, for example, for the double slit experiment, probability does the electron arrive at a certain point, or does it describe the position of an electron in any situation?
Good. This describes the probability that the electron, that if you were to measure the electron, it would be at the position x at time t. Okay. In particular, one of the things that's very important, and this is something we discussed earlier when we did the double slit experiment, is that you can't interpret, so you shouldn't be interpreting psi as telling you at any intermediate stage of the experiment where the electron is. So, for example, in the double slit experiment, it's very important in order to get this interference pattern that we not observe the electron while it's going through one of the 2 slits. Okay. Because if we do, we'll see that it goes through either one slit or the other slit. It's only at the end of the day when we are calculating the value of the wave function on the screen on the other side of the double slit experiment that we want to calculate the square and interpret that as the probability that we see the electron at a given point. So when I say we interpret psi squared as the probability that the electron is at a given point, implicitly what I mean by that is that we are performing a measurement, and we're measuring the position of the electron, and then the value of psi squared is the probability that we obtain the result x for that position measurement. So the subject of what exactly an observation is and what a measurement is in quantum mechanics is a little subtle, and that's what we're getting towards in this development. That's what I'm getting towards, yes.
Could we pretend we did a bunch of experiments with different keys and then look how the probability distribution is different for each one to get an idea of how it's moving?
Yes, you could. But, for example, the answer that you get will depend on what sort of measurements you make. So, I mean, this is the amazing thing about the double slit experiment. I mean, which is the truly mind-bending thing, which is that, let's say that we take an electron and you send it through the double slit experiment, and if you measure where it is as it passes through the two slits, then you'll see that it goes through either one slit or the other slit. And if you do it 1,000,000 times, you'll find that there's some sort of distribution of results that you get. So you would find that at the end of the day, the electron always goes through one slit or the other slit. And so if we did what you had suggested, and we said, well, let's just continuously measure the position of the electron as we're performing these experiments, you actually get a different answer than you would if you just never measured it. Okay? In particular, if you don't measure which slit the electron is going through, then what's going to happen is that you'll allow it to interfere with itself. Okay? So the reason why this happens is that the act of measurement itself disturbs the system that you're trying to measure. But it disturbs it in a way that we can quantify. And in particular, it's something that we will quantify over the next week and a half or so. Yeah. Okay. But before we can get to that, we need to understand exactly what sort of objects it is that we are dealing with. So in particular, we've seen that we have some wave function psi, which must obey a linear equation. And the simplest sort of linear equation the simplest one we could imagine writing down will be an equation where you just take the time derivative of psi and set it equal to something involving spatial derivatives of psi. So remember, a wave equation is always of the form some time derivatives of your basic dynamical variable, such as the height of a wave away from its equilibrium position, equal to some spatial derivatives of that object. So the simplest wave equation that you could imagine writing down will be an equation where d psi by dt is equal to something that I will call h psi, where h is some sort of differential operator. And the statement that h is a differential operator is just a fancy way of saying that h psi depends on psi and its x derivatives. So, for example, we would expect that h psi will be equal to, for example, something linear in psi that depends on psi and its derivatives. So, for example, it will be something times psi plus something else times d psi by dx plus something else times the second derivative of psi d psi by dx squared plus so on and so forth. Okay. That's schematically the sort of equation that we would like to write down. And we know, because electrons exhibit interference, that it has to be a linear equation, which is why there's only one power of psi on the right and the left-hand side of this equation. And what we would like to understand is how the various derivatives appear in this equation. And there's a bit of conventions here that we introduce when we write down this equation. So there's a factor of I, which is pure conventions. Okay. There's no physics in there. And there's a factor of h bar, okay, which is also conventional. And the reason why we include that h bar there is for reasons of dimensional analysis. Because h bar has units of energy times time. So if we have an h bar there, then h will have units of energy. So h has units of energy. And in particular, we'll see that there's a sense in which it is energy. It's nothing more, nothing less than energy. Okay. So there's one more thing which we can say about the form of this equation, which is that it must respect the fact that the sum of all probabilities has to be equal to 1. So in particular, the integral dx of psi squared from minus infinity to infinity has to be equal to 1. That's just a statement that the total probability density that the electron is anywhere has to be equal to 1. That has to be true at all times. So we can take the derivative of this equation with respect to time to get some idea of what this operator h should look like. So let's take the derivative of this with respect to time. Oh my Lord. So 0, which is the time derivative of 1, okay, is the time derivative of the integral from minus infinity to infinity dx of the absolute value of psi, which I'll write as psi star psi. Okay. Star is just complex conjugation. So this is equal to the integral from minus infinity to infinity dx of the time derivative of psi star times psi plus psi star times the time derivative of psi. And remember, I'm assuming that my wave function obeys an equation of the form I h bar times psi dot is h psi, where h psi is an abbreviation for something involving psi and its spatial derivatives. So we could just plug that into this equation, and we'll see that this is the integral of minus infinity to infinity of, what is that? Well, we could just take the complex conjugate of this equation here to get I h bar psi dot star is equal to the complex conjugate of h psi. So let's just pull out an overall factor of 1 over I h bar here. And we get the integral from minus infinity to infinity dx of, sorry, and of course there's a minus sign there because the complex conjugate of I is minus I, of minus h psi star times psi plus psi star times h psi. So this has to be equal to 0. Yes?
Is there supposed to be a dot over the second side?
Psi, yes, there's a dot. That's a dot. It's a very small dot. You couldn't see it. Yes. Yeah, dot there. Good. Any questions? Any other questions? Okay. So this will constrain the possible form that our operator h could take. So remember that schematically, we expected h psi to be something like a times psi plus b times d psi by dx plus c times the second derivative of psi with respect to x, and so on and so forth. So let's ask then whether that form of h that we have written down is consistent with this equation here, which just says that, well, the electron is can be neither created nor destroyed. It always has to be there at all times. So if you just consider this first term here, and you plug that into this equation, then you see that in order for this equation up here to be satisfied, a has to be a real number. Okay? Because if h psi is equal to a psi, then this term here is just minus a star psi star, and this term here is a psi, and so everything will cancel out, provided a is real. What about the second term? And actually, I should mention that a can be real, and it can be any function of x. So a, let's say a is a real function of x. But let's now consider that second term. So if h psi is b times the derivative of psi with respect to x, let me write it out, d psi by dx, then what we have in this equation up here is the integral dx of minus b star d psi by dx star times psi star plus psi star times b times d psi by dx. And we would like to ask under what circumstances that could be equal to 0. It doesn't look like it's equal to 0 at first sight. But if b is equal to a constant, then this, so what we can note is that this term here can be integrated by parts. Okay? So that this is equal to the integral dx times minus b star, or let me write it this way. So it's psi star times d by dx of minus b star, there's no star there, psi plus psi star b d psi by dx. So just integrating that first term by parts. And this will be equal to 0 if b star is equal to minus b, i.e. if b is an imaginary constant. Now, I should make one comment here, which is that when I integrate by parts, in principle, I should worry about a boundary term. Okay? Because this is, what is it called, Newton's law. Okay? The integral of derivative is equal to the function of a function is equal to the function evaluated at its boundary points. No, that's the fundamental theorem of calculus. Sorry, that's one of those. I'm assuming here that because psi has the property that the integral of its square from minus infinity to infinity is equal to 1, that it has to vanish pretty rapidly as x goes to plus or minus infinity. So I'm assuming here that because psi it vanishes sufficiently rapidly, so do its derivatives. Now, in the case of a free electron that can be absolutely anywhere in space, there are some subtleties that will actually make this a little bit more tricky. But for most cases, this is a perfectly reasonable assumption. So what we see is that our Hamiltonian, sorry, I didn't use the word Hamiltonian, the differential operator h acting on psi has to be some function of x times psi plus, let's just call it I times b. So, or I guess I'll just call it b times d psi by dx, where b is a, scroll up, good. Where b is a purely imaginary constant, then there was the second term c times d psi squared by d squared psi by dx squared. And just as we saw that b had to be imaginary constant by integrating by parts, c has to be a real constant by integrating by parts twice, plus so on and so forth. So this is imaginary. C has to be a real number, just because you could go through that exact same manipulation that I went through above, and you would get a cancellation only by doing that integration by parts twice. And you get two minus signs because you do two integration by parts, so that C had to be real, unlike B, which had to be imaginary, and so on and so forth. Now, of course, I've already spoiled the surprise. So H has a very natural physical interpretation as the energy of a system, or as what's called the Hamiltonian of a system. And in order to determine precisely what H we need in order to describe our system, we're going to need to be more specific about exactly what kind of electron we're talking about, and exactly what kind of properties we want the system to have. So next class, what I'll do is I'll use some very basic physical principles in order to determine what these constants B and C are, and what that function A is, and indeed what their physical interpretation is. Okay. I'll see you guys all on Monday, because you have a special super surprise lecture on Friday.